Hi everyone, I'm Yuriy Reznik. I run research at Brightcove, and I'm going to talk today about topics that is sort of difficult to talk about. It's measuring QoE, and why it's difficult to talk about it because it's a very loaded and deep domain of knowledge with much research and much going on, several standards activities going, several companies existing, producing their metrics. And there is a lot of what I would say smoke and mirrors. And so instead of kind of adding to that, what I will try to do, I'll try to bring some very basic things that known from literature, or that could be proven mathematically, or that could be just followed by simple applications of logic, and try to bring some things that hopefully will be useful to the community. And basically my message here is don't expect miracles. There are lots of things out there that claim this next best greatest solution with artificial intelligence and other stuff. Well, sometimes real intelligence also helps. So I encourage to stick to the latter one. So now let's try to look at where we are in terms of sending videos eventually over streaming. And you see it's kind of a complex system because it doesn't start with streaming, which is just the last block subset of it at the bottom of this diagram. The content usually starts somewhere else. It's done by it's created by studios, or it originates from remote and field production and broadcasts. Then it goes through a broadcast chain of some sorts. It goes through playout. It goes in form of channels to the air or through other distribution channels. And at some point, it could also reach cloud by means of connecting another contribution encoder or any other encoder that's available to the existing chain and broadcast, and basically converting it in formats that could be pulled later by cloud platform. And then cloud platform does the rest of actually doing encoding for streaming and delivering it in a streaming form. But the important thing in this diagram is to understand that when we talk about quality, it's not only the encoding at the last mile that matters. You actually, before you're even gonna get to this last mile, there will be at least 2 other encoders in process, and there will be several format conversions that will happen. In broadcast, if it goes through broadcast workflow, most likely it's gonna be in interlaced or telesync forms. Then you'll try to de-telesync, then you'll try to resize it or do frame conversions. All those things will add extra noise to it, and then of course there are other things that might happen with content. So with streaming, the content is encoded, placed on origin services and origin servers. Then it's pulled by clients through CDNs, and of course CDNs are not perfect. Origin servers are not perfect. The clients with their adaptation logic can also be confused, and then there is user behavior that affects what happens on clients at the end. So basically, problems that would eventually affect QoE could happen at every stage in this fairly complex diagram. And this is just like a very rough sketch of what might actually be happening in reality. In reality, it might be even more complex. So the first morale here is that, if you're looking just at last mile encoding, that's not the main source of problems in many cases. And in many cases, you just don't know what's going to happen before or after. Next, let's try to take a look at sort of factors that affects QoE. And on a scale of things, I think that codec introduced noise actually belongs to the very last element of it. And there are much bigger things and much more obvious interruptions of user experience that might be happening. So number one is that playback might not be happening at all. User might just kill the player the moment it starts playing pre-rollout of some sort, or in many cases playback doesn't start because of some other reasons. If it goes through player initialization and then player has autoplay and there's volume that is not muted, and there are many other conditions under which playback just wouldn't start, and this is a number one factor that is important. Second, of course, is continuity of playback. So playback, of course, might not be continuous, the network might fluctuate, and sometimes player logic might be faulty. The network is still okay, but it, for some reason thinks it's not, and it stops playing, starts buffering. Or sometimes it loads one stream and starts loading another stream, and then it runs out of bits and forgets that there is another one that it's already loaded. So continuity of playback is important, and it could be interrupted by buffering, it could be affected by stream switches and other factors. CPU could be overloaded, and decoder starts dropping frames, or renderer starts dropping frames. Things of this nature. And then go parameters of viewing setup. So things that really matter are actually viewing angle, which is basically angular span between eyes and the display, or actually window on the display where video is being played. Second is this is angular resolution. This is not resolution in pixels. Resolution in pixels is kind of almost, it's just a not properly defined metric. What matters from quality of experience perspective is angular resolution that's measured in cycles per degree. It's basically translation of within that viewing angle how many cycles of content could be reproduced. And then, of course, there are parameters of displays, things like brightness, contrast, which of course affected by ambient light, background light of any sort, so on. And only at the bottom of this pyramid are things that we think are, at least in codec world, we think are important, and those are codec introduced noise. And also right there are conversion artifacts, which in many cases are even more significant. Take a poor deinterlacer and compare it with encoding at 1 dB less, which one is worse. So this is like a top level laundry list of criteria, and then let's take a look what could be measured where and what we actually know. And as I've shown in first slide, the system is actually typically includes multiple encoding stages, and then there are other stages at which we might learn something about quality. The last one, of course, is player. Then there is a CDN or origin, basically server-side monitoring solution of some sort. And then there are, of course, encoding points. And as you could see, even at player, we don't know everything that we need to know to be able to understand what quality of experience it is. At a player, actually, we know the most about relevant factors. We know angular size, angular resolution, we know parameters of display, but we don't know codec noise, or we don't know anything about accumulative conversion artifacts that happened before that. And likewise, if we're at encoding stage, well, at encoding stage, of course, we can measure Pearson R or SSM or something else about how we damage the signal, and we could infer if there were conversions before or what we did specifically. So those things we could measure at coding, but when we do encoding, we really don't know what will be angular size, we don't know what would be angular resolution, and we don't know what would be other parameters of reproduction setup. We sometimes assume like BT500 reference reproduction setting or mastering room during post-production as a setup, but in fact, that's not gonna be happening in real life. What's gonna be happening in real life is same stream could go to at least 5 different categories of devices. It could go to TV, which is probably best aligned with that reference setup, but it could also go to a PC or a laptop. And on PC, somebody could watch video full screen, or it could watch it like in a corner in a small window. we don't know it. Only player will know. Similarly, if you look at tablets and mobiles, also the characteristics are quite different. And what it brings us? Well, if we now look at like ballpark numbers of what would be the typical viewing distances, display sizes, and other characteristics, we can compute what would be, again, like median viewing angle to each category of devices, and also angular resolutions if you are trying to throw video encoded at a certain pixel count. And just to take a look at TV screens, of course, 33 degrees is about reference setup that is usually expected. But then if you look at resolutions, angular resolutions achievable, then with 1080p we achieve about 28.3 CPD, and with 4K it becomes over 50. Now, and that is when maximum resolution, visible resolution, is just about 48. So from here we clearly see that 4K is obviously an overkill. 8K is beyond anything that is even close to being reasonable. So at least for a setup that is assuming 3 heights viewing distance. And similarly, we can see that these characteristics are different in other cases. Now, how do viewing angles and angular resolutions affect subjective quality? Well, it's actually a well-studied subject, and there was a seminal paper by Westerling and Roofs published in '89. It's been confirmed by many subsequent studies. It has over 100 citations. Barton and his book arrived at same results using completely different method. And what it basically says, so they conducted experiments by asking people to look at screens from different distances with different viewing spans of image, and also by projecting images at different resolutions. And what they have established is that actually the subjective scores are increasing proportionally to logarithm of viewing angle. That's one discovery. The other is that this angular resolution quality of experience also is increasing, but it's starting to saturate at about 25 CPD. So, and they even provided exact mathematical formula for this. The page includes exact link to this paper. Please feel free to take a look. And but when we started working with that model, what we discovered is that the range of angles and resolutions which they tested was somewhat narrow, and we wanted to expand it. So we looked at more recent data, and we also did a bit of playing with Mathematica and came up with this model that fits Westerling Group's experimental data with super high accuracy. It's like RMSE of 0.02 at 1 to 10 scale. It's less than 1% in accuracy, but on the other hand, it behaved nicely. It basically converges to 0 at 0, and it saturates at a certain point. It saturates when angular resolutions go beyond 25, as that model suggests, and in viewing angles, it saturates at about 60 degrees viewing angle, which we know because field of view of human vision is about 120 degrees, and even that is kind of it's extremely bothering to look at screen with such a broad viewing angle. Your accommodation doesn't work nicely. At front screen, you will focus on one distance. When you look at the angle, extreme angle, it's kind of you need to refocus. And by the way, in TV specifications for movie theater, in specifications for movie theaters such as THX and SimTSpec, they actually also provide a certain range of viewing angles that is considered recommended. So this model kind of captures this, and it's conforming to experimental data that we've seen in literature. Now, what this model tells us? Well, it's actually quite useful. It can predict, for example, when stretching a small resolution video on large screens, and large screen is not going to help. For example, assume that you're sitting in the front of a PC display, and it has 96 dpi pixel density as standard for most PC monitors. You're looking at it from about arm length, and now you have, say, 270p video, and you're trying to blow it at full screen. And let's assume that full screen is 1080p. Well, turns out your quality is not going to look any better. As you will upload it to full screen, you will obviously see that the video is low pass, so there is no details there, and your quality is actually will be worse. Now, if we look at the other example, where, for example, you have 540p and now you're projecting it on a screen with Retina display, for example, on iPad, and you do same exercise, well, turns out that in this case, going to full screen is actually improving quality. Why? Well, because you started with more pixels, and at that particular viewing angle, it's still appreciable, and the quality is better. So it's a very useful model connecting two super important parameters of viewing setup, which is viewing angle and angular resolution. By the way, the formulas here below show how to compute. So the phi is how would you compute viewing angle, and U shows how to compute angular resolutions in case of both full screen and in window representations. So where do we go with this next? Well, let's now try to combine this model with codec-introduced noise. And how to do it? Well, let's try to take Pearson R and let's do the same thing. Basically, it's the same model where inside of this chain we added extra factor, and now this factor has saturation parameter and gain parameter for Pearson R. And what it does, well, on we pulled the Netflix data set, which is commonly used these days to test different quality metrics, and we tuned this model to be conformant with this data set. So we know that the data set, when it was produced, they described which viewing angles they were used. So we tuned this model to that operating point, and we also left the variation along viewing angle to angular resolution, that ratio to be the same as an original Westerling Group's model. So the model is basically the same as before, but we just added extra dimension. And if you look at the three-dimensional plot, it looks wonderful. This model shows RMSE of 0.294 on 1 to 5 scale, and that's actually better than VMAF that was produced and tuned for same data set. And now why you would ask it works so wonderfully? Well, because we are doing multi-dimensional fitting. We look with noise as extra dimension and resolution another one. If you just try to match all data to either resolution or noise, you look at those plots below and you see how poorly they correlate. So the RMSE for those is about 1 for Pearson R and 0.7 or something for resolution. But if you try to model in two-dimensional space, well, it turns out there is a structure between those data, and then this two-dimensional model just picks the structure better. Same with SSM. We could use either Pearson R or SSM. With SSM, we use a little trick. Instead of connecting it directly, we use extra compounder, which is lambda 2 SSM times some factor -1. And it basically translates it back after this front logarithm linear domain in the main region of interest. And again, it fits very nicely and better than VMAF, and we see same effect. So you could use either Pearson R or SSM. You can use both, and that's actually be even better. Now, there is a side fun effect here. So if you, by the way, let me pause before. Do you guys have any questions so far? Did I lost everyone?
Andy here.
Yes.
You said that SIM is better than VMAF for this assessment, but you could use PSNR. Well, no, wait a minute. What are you saying? That PSNR has got no subjective element to it.
Same as SSM and same as VMAF. So basically what I'm building multi-dimensional model where I'm taking either SSM or PSNR as one of the parameters. And I'm treating these parameters only as ones that measure codec noise. And I always measure PSNR, SSM, and same resolution at which content is encoded, not upscaled, just the same as it is encoded. It's pure codec noise. And then I add resolution and recalibrated the resolution, calibrated in CPD, cycles per degree. This is another dimension. And there is actually a third dimension, which is viewing angle, which is in this data set is fixed. So it's besides the point. But when I factor this as two additional dimensions and do the fit, I actually get pretty decent results. Does it make sense? Good.
Hey,
yeah.
This is Frank Charmello here. I'm curious. The thing that's kind of interesting to me is kind of the traversal of the graph there. Are there interesting observations you have around your example anecdote around, hey, a particular encoded, a particular resolution actually improves in quality by going full screen, but in other cases you get quality reductions. I'm curious if this kind of yielded some insight or some anecdotes or rule of thumb that you're seeing around how to kind of traverse that quality graph when you have video that varies in both resolution and playback size, especially on the web, with people kind of being so easy to change your browser window. If there's kind of interesting user recommendations you could make there to say, hey, actually, if you maximize this, you're going to get a better picture quality, or if you make this smaller, you might get a better perceived quality.
Absolutely. So there are tons of utilities that you could extract by using this model, and it could go into extra logic inside of player. It could also go in the logic of kind of looking at statistics of how people typically use their players at the encoder side and try to figure out what you can do creatively at encoder side to match the preferences of users. But basically, it is a very powerful model, and it's been out there since 1989. And I think it's time we use it, and all ingredients are there. So thanks.
Hey, Yuri, one before you continue, Gary, do you have a question? I see you raised your hand. And you're muted, by the way.
Right. Yes. Yeah. I was just going to observe. You have chosen PSNR as a way to plot this, and translating that to bit rate, I think, is an interesting aspect. Netflix in particular has and now at Facebook, they've been doing some work where they talk about what they call the convex hull of should I lower the resolution if I have a certain bit budget, should I code at this resolution, or should I lower the resolution and code at the same bit rate at that lower resolution? And there is kind of the same idea of a multi-dimensional surface there that you're trying to optimize for, because if you operate a video encoder at such a low bit rate that it can't keep up with the resolution you're feeding to it, it's better to lower the input resolution and just upsample the result. And I think that ties in somehow to what you're talking about here.
Precisely. So this is another potential application of same model. And what we are doing here is decoupling Westerning roof model with codec noise as additional dimension. And we're showing that this coupling actually has very good fit to experimental data. We actually tested it on about 7 data sets, and the results are very promising. And of course, internally, we use a little bit more sophisticated model. We use several criteria of codec introduced distortions, but the concept is the same. You could couple them all together in a single model, and it will tell you integral expressions saying what would be the QoE considering all those factors. Thank you very much. It's a perfect application. So if I can, I'd like to move on, and I want to bring one fun side effect. And this is just fun. So if you would look what we just did with SSM we basically did this thing. We took some mean function, which in that case was actually geometric mean or power mean inside of the logarithm. And then we took another function, which is monotonic, and we basically folded the mean. So we basically took a mean of inverse of this function and then took that function on the top. So more specifically, you could think of this like this. We took a geometric mean, and the compound functions that we plugged in is logarithm of 1 plus x. So what this boils down to is this formula that's inside of this green triangle. And what this thing is, what the heck it is? Well, if you guys know what it is, let me know, because I think it's actually quite interesting. So if both x and y are small, it actually converges to standard geometric mean. And if x and y are sufficiently distant from 0, then it converges to arithmetic mean. So it is a mean that falls right in between of those two. It doesn't belong to family of power means and any generalized means. It's kind of interesting, but that's a particular flavor of means that we happen to be using in producing this quality matrix. And why it's useful, because we know that at the boundaries of a quadrant, we really want each quality parameter to force entire quality expression to go to 0. So it has to become more like a geometric or power mean. But inside of the body of quadrant, we know from experiments that it behaves as additive model. So that's, if you guys know how this thing is called, let me know. Otherwise, you can call it Yuriy's mean. I wouldn't mind. Now, there was a question about using Pearson R as SSM and which one is better. Well, folks, I want to tell you that there is no magic there. So let's just look at equations and do a little bit of math here. So if you look at Pearson R, it's basically a logarithm of MSE, which is internal 2 norm of 2 images. If you look at MSE SSM, it's this funny formula, which is defined not on the entire image level, it's defined on patch level. So you compute it on every patch, and then you look at average of all patches over the image. But even if you compute it at patch level, let's try to see what would be patch level relationship between Pearson R and SSM. So if we do a little bit of math, we will realize that MSE could actually be expressed in terms of those parameters that I used in SSM, and those are like local DCs as well as variances and covariance between patches of those images. And if we can express MSE through these parameters, then we could replace the covariance element in the SSM metric by MSE minus the rest of them. And as we do this and we simplify the expression, we arrive at this formula right below. But now we notice that this mu x minus mu y squared is used in both factors, right? So if we assume that this thing is delta, and this is, by the way, DC level difference between two images, and we assume that that DC level difference converges to 0 faster than anything else. And why it should converge faster? Because images at large are flatter type of things. Then what it boils down to is this. It boils down to 1 minus MSE divided by energy of both blocks. So this is effectively a funny computed version of signal to noise ratio. Actually, it's a noise to signal ratio, but you could express it that way. And basically, so what it tells you, well, of course, you shouldn't expect miracles from this metric. It's a signal to noise ratio. By the way, same. It relates to MSE same way as Pearson R, and also a similar connection exists between VIF and MSE. So really, when we talk about those pixel level metrics that out in the literature, and you just apply different norms to compute them, no miracles should be expected there. They all will be similar in some sense, and there is just simple mathematics that explains why. Now, why using both PSNR and SSM could be useful is because of relationship on signal energy. So since there is this normalization and this signal energy could vary from one sequence to another, then using both of these parameters could give you a better better discrimination power if you are trying to design a multi-dimensional fit model to capture the quality. So that's another aspect that I thought might be useful. By the way, there was a paper by Har and Zhu in 2010 at ICPR on connection between PSNR and SSM. They actually didn't come up with the same equation. Their equation is different. I think the asymptotic I'm giving here is actually more accurate, and their conclusion was different. This asymptotic shows that this is actually a signal to noise ratio in the high precision region. So next is another thing that I mentioned at the beginning, that when we talk about noise propagation, it's not the last encoder that you should really worry about the most. In many cases, hopefully that's the encoder you have to worry about the most, but in many cases, the signals that you receive is actually coming from at least one or two generation of encoders before. And then the question is, okay, now I could produce, encode the signal. My PSNR of the signal will be X, but what is the PSNR of signal relative to the original? And actually, we can answer this question. So if we know both PSNR of prior encoder and current encoder, and prior was encoding the originals, and we know that PSNR is effectively a logarithm of MSE, and MSE is a metric, then for metric we could use triangle inequalities, and that gives us this, this formula. Now, one interesting, so we could actually measure propagation of noise, and we could estimate the PSNR that will affect quality at the last chain if we know prior PSNR estimates. And when we do quality QoE estimates, what is important is actually not to get the PSNR or SSM of last encoder, but to try to figure out what would be the distortion relative all the way to the source. Now, one side effect of this inequality is that if we assume that this last generation encoder is the one that is generating most noise, or at least as much noise as prior generator encoder, then what it boils down to is that the PSNR between original and output can be bounded then by PSNR of your last encoder minus 3 dB. So basically what it tells you is that if you want to target certain level of quality, then please add 3 dB in your mezzanine encoding, and that's a simple rule of thumb that could be followed to make sure that at the end of the chain you're not going to suffer too much. So building complete model, and this is my last slide. So far what I have shown a few things. So how to build simple models factoring parameters of viewing setup, such as viewing angles and angular resolutions, and also codec noise. I also talked a little bit about what is the difference between PSNR and SSMAs, and also how to estimate what PSNR could be if you have multi-generational encoding. But now there are, of course, many other parameters that should be factored in complete expression, and there are actually several examples of how to do it, and probably most recent one worth checking is ITU standard ITU P1203, and specifically part P1203.1 deals with the video artifacts and introduced distortions and quality impairments, and P3.12 or 3.3 does this, deals with integration of all of them together. And they could be used as a good learning material and reference and seeing how that kind of those more complete quality estimation system can be built. But in principle, what I must also say is that none of these existing techniques is perfect, but by any extent of imagination. They all rely on certain heuristics. They all, at the end of the day, trying to do the fit to some finite set of experimental results. Those experimental results and conditions may or may not match well as the specifics of your system and type of devices, type of users, and type of content that you're dealing with. So basically, doing research yourself is always a good thing in this domain. And also, it's an evolving topic. There are still many things that still need to be done at system level overall to have a better handle of it. So for example, carriage of metadata, specifically all the way to clients explaining what are the noise characteristics of streams such that clients can do proper estimation is extremely important. The current systems such as Dash and HLS, they don't have this type of capabilities. They should be added. Similarly, within the kind of multi-codec framework, those parameters will be useful. If you don't know it, you have to estimate them, and if you estimate them, you're really making guesses, and things can be done better. But in any case, I hope a few things I brought are useful, and thank you very much.
Thanks, Yuriy. That was great. Where do you see you taking this next?
Well, we have a Play conference coming in a couple of weeks.
So I should tune in.
You should tune in. We'll talk about some products and some product updates there. And then there is going to be Streaming Media West, and so there will be some things coming.
Okay.
But I'm hoping that just basic science that I'm sharing is useful, and I just encourage everyone to study the subject and learn more about it and do experiments. We are all researchers. It's a deep topic. QoE is the deepest topic of them all that exist in delivering video, I think.
Hey Yuri, I had a quick question. I'm very much in that camp. Nothing gets me out of bed in the morning like video quality. Have you looked at temporal aspects of this work and how that affects like temporal masking or artifact smoothing out over time? How that kind of plays in here?
Absolutely. So basically, of course, when I used Pearson R, I used compound statistics of the over entire sequence. That's of course a very inaccurate way of doing it. So what you really should do is look at frame level statistics, and you could look at either histograms of the statistics, or you could apply certain smoothing filters to capture significant variation of qualities that might become irritating. For example, you will have fluctuations between PSNRs and B frames and P frames. So they just encoded at different PP levels, and that is to be expected, right? But since B frames are, appearing at high frequency, some of this noise flickers that they introduce becomes masked and it kind of shaped an invisible domain. Now, if you apply a temporal filter on this noise statistics, that will remove the kind of noise introduced by different frame times, but it will still leave a fluctuation of qualities that were probably deficiencies of encoder in handling different scenes, or in kind of doing one pass operation where you really need to do two pass and you really need to reallocate bits efficiently. So basically, absolutely, temporal statistics must be measured, and of course, you know, there are more advanced metrics. You could look at using masking. You could use two-dimensional contrast sensitivity models. By the way, applying them in temporal domain is a bit easier because so this spatial domain, you really need to have calibration. You need to know how your pixels translates to cycles per degree. This temporal domain is actually easier unless your renderer is doing a sampling somewhere down the chain. So, but absolutely. So extra parameters. Extra.
Andy here, again, something is breaking my intuitive sense.
Mm-hmm.
Coverage of soccer, European football,
Mm-hmm.
might have the exact same energy level as handheld nature footage of running through the jungle trying to follow some animal. But the latter is going to have enormous subjective masking. But any artifacts in panning back and forth across the soccer field, again, energy levels might be the same, but it has much less masking. If you're not using SIM, you're not honoring the human visual system masking, which is substantial, at least in that hypothetical case.
Well, Andy, as I told you, don't expect miracles from SSM, VF, or other simple metrics. Until you know the translation between your pixels to cycles per degree, you just cannot apply existing science precisely. So all this metrics measuring is very rough approximations, and I was showing you what SSM is measuring. It's basically measuring signal-to-noise ratio. To which extent signal-noise ratio is better indicator of encoding gracefulness as opposed to pure SSM, is of course, or a pure amount of noise is of course dependent on content. But what I want to say is that none of these metrics are measuring it precisely. If you'd like to use metrics that tries to measure some of these effects precisely, it will be VPD, Visual Differences Predictor of Scott Daly, or Tektronix PQR, which is based on Lubin's model. But those are pretty sophisticated tools. You need to calibrate them precisely, and you also need to know what to expect from them. So those things can be used. They could be applied, but to apply them right, you probably will need to do it in aggregate. You need to look like a distribution of possible viewing environments across population of viewers. Then you compute your quality score for each type of viewing environment, and then you do the aggregate of this back to the total score. But I think you know, overall effect will still be much less precise as opposed to the case where you actually know exactly your setup. So in any case, quality is a nice topic. There could be lots of things said about precise tools and models, but they are super difficult to use, and they are good in such a narrow use case scenarios that it almost kills the utility of these tools. So. And if you're trying to do something simpler as well, then you end up with Pearson R and SSM, and that's what.
That's great.
Yeah, but hopefully coupling it also with westerning roofs and some other models. By the way, like the saturation at around 25 CPD in westerning roof models, that actually could be refined. So there is a Barton model showing the contrast sensitivity model. It has same saturation, but there are relationship of that saturation point, for example, with respect to the brightness of the display and and parameters of ambient light. So basically, for HDR, it will be somewhat different, and this can also be accounted. So basically, there is no shortage of science that can be applied here.
Fantastic. Thank you very much, Yuri. Is there another question?
Yeah, one comment, Gary here. I keep thinking about your comment about DC differences going to 0 faster than other elements of the error. I wonder if that's really a valid assumption. I think when we do video coding, we kind of generally distribute the noise not so differently among different frequencies.
When you distribute not well, but when you do video coding, your DC goes away first, right? It goes away at prediction. It goes away at motion vector prediction. So you extract.
Yeah, I guess that's true. The prediction becomes easiest for DC. Yeah. But but the quantization we apply to one frequency or another is often not so different.
Yeah, that's correct. So there is, of course, this matrix that older generation standards were allowing to use. And the trick with using that matrix is, again, you really need to know the reproduction setting to create it correctly. Because
and for that, we would tend to put more noise in the high frequencies than we do. Yeah. So in that case, the DC would go to 0 before the high frequencies do. Yes.
Well, my intuition here was this. The images are it's non-negative signals, right? And if you look at non-negative signals and you look at spectra of non-negative signals, then what applies is so-called Lucas bound, or the Bose-Katz-Lucas, which basically shows that disease goes high, and then there is like first frequency, second, and so on, and they basically decay as cosines of certain angles, and so just non-negativity of the signal suggests that it should be somewhere there. But on local scale, of course, it could be different. And depends on size of the patch. If the size of the patch is small, of course, you might just hit an edge. Right.
Okay. Yeah. Thank you.
Thank you.